Assalamu alaikum, dear students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the 14th lecture of Thermodynamics 2. Lecture 14. The contents of lecture 14 are entropy, property of system, entropy of a pure substance, increase of entropy principle, entropy balance, isentropic process, entropy generation, numerical problems, and conceptual questions and answers. Entropy, property of a system. So here is a definition of entropy, that entropy is a measure of molecular disorder or randomness of a system. So as you can see on the right hand side, small molecules are shown in a dot, small dots are shown, and as you can see, the location or the position of molecule is changing with respect to time. So there is a disorderness or randomness in the position of the molecule that comprises a system. So entropy is the measure of that disorderness or randomness of system. Concept of entropy arises from second law of thermodynamics. So we have already discussed about the second law of thermodynamics. So as you know that heat is a low grade form of energy, so all thermal energy can never be converted into 100% of work. So in the right hand side it is written that Q or heat is equal to work plus waste. So certain amount of heat energy will be converted into work, whereas rest will be is rejected into the atmosphere or ambient as a waste. So for example, if we take an example of an engine of automobile, so it is a fuel and oxygen mixture is introduced in a piston cylinder, and after the combustion a certain amount of work is reduced from that process, which is utilized to displace the piston within the cylinder, whereas the rest amount of energy is rejected into the atmosphere through the exhaust valve. So it is written that the amount of energy is the summation of work done, and waste means that amount of energy is rejected into the atmosphere through exhaust. So as we know that matter exists in three phases: solid, liquid and gas. So the molecules of solid are tightly compact with each other and their motion is constrained. So as you can see that the molecules are vibrating about their mean position and are not uh, change are not vibrating vigorously. So the entropy of solid is least. In the middle you can see a liquid, and the molecules of liquid are vibrating more than the molecules of solid. Therefore, the entropy of liquid is greater than the entropy of solid, as the motion or randomness in the liquid is greater than the solid. And the third phase is gaseous phase. So as you can see that molecule of gas are vibrating vigorously, and disorder or randomness in the molecule of gas is much greater than liquid or solid. Therefore, the entropy of gas is greatest. So here solid entropy is less than liquid entropy, and liquid entropy is less than gas entropy. So if we take an example of water, so here in solid phase is ice, so the entropy will be least, and in liquid water the entropy will be greater than solid but less than vapor. And in gaseous phase water exists in vapor form, so the molecule of water vapor will vibrate vigorously, and there is much greater disorder or randomness in the system. So the matter that composed energy will have an ordered form of energy and disordered form of energy. So if we are talking about water, so the certain ice, that water exists as ice in solid phase, therefore the certain ice will have an amount of energy. That energy will be a sum of ordered energy and disordered energy. So when we will be talking about ice, then the ordered energy will be greater than disordered energy. And as we move to the right and we have liquid water, then the disordered energy will be greater, will increase. And when we will be talking about water vapors, then the disordered energy will be maximum. So energy will be a summation of ordered energy and disordered energy. So if we are reducing or getting work from that energy, then useful work will only be obtained from that ordered energy, whereas disordered energy will only give waste work. So that wastage amount of energy, we call it entropy. So hope you will get a comparison of all three phases of matter, their increase and decrease of entropy, how they are increased, and energy is the sum of ordered and disordered form of energy, and useful work is only obtained from that ordered form of energy, whereas disordered form of energy is wasted into the atmosphere. And from second law of thermodynamics we can comparison we can comprise all that the heat supplied is the summation of work and waste, and that waste is known as entropy. Heat transfer. Heat is a form of disorganized energy, and some disorganization will flow with heat. Heat is associated with entropy. So in the previous lecture we have already discussed about the heat that is a low grade form of energy. So when we are talking about entropy, then we will use the term disorganized energy. So heat is a disorganized form of energy, and some of disorganization will flow with the heat, and entropy is associated with heat transfer. So work transfer, it is entropy free and no entropy is transferred with work. Work is not associated with entropy. Work transfer is an organized form of energy. So in the previous lecture, we have recognized work as a high grade form of energy and it is entropy free, and when we will be talking about entropy, we will target work as entropy free. So work transfer is organized form of energy and no entropy will flow with the work transfer. So here is a mathematical relation of entropy. So entropy is represented with the S, and usually we will be talking about change in entropy. Entropy is also a state function. So at a particular location, at a particular state, you can find the value of entropy. So usually we will find the value of entropy from steam tables. For for example, if we will be talking about steam, so when you will be, you know the temperature of steam. Let's suppose a steam is present in the superheated region and its temperature is 250 degrees centigrade. So you will go into the steam table and in 250 degrees centigrade temperature column you will see a number of values, and in for example specific volume, and then you will see the value of entropy in that session as well. So usually when we are talking about entropy, we are interested in finding the value of change in entropy. So the symbol D represent change. That ds mean delta S or change in entropy. That is greater than equal to dq by dt. So D also represent change. So change in heat with respect to temperature. So the well the change of entropy represented by change of heat content with respect to temperature. So for the first pro, the first mathematical form is used for any process. So first form is true for any process. In the second relation, it is written that ds is equal to dq by dt. So in the first, that is greater than equal to. So we we can reduce that result into two. Either ds is greater than dq by dt or ds is equal to dq by dt. So we are in the second relation we are discussing the first form when ds is equal to dq by dt. That can only be used for reversible process. So ds is equal to change in entropy will be equal to change in heat content divided by temperature for reversible process only. And change in entropy is greater than dq by dt, or change in heat content with respect to temperature is only apply for irreversible process. So as you know that in the real world usually all processes are irreversible. However, when we will be talking about certain ideal cases like as you have studied Carnot cycle, so we will be utilizing this in the relation that is in the middle, ds is equal to dq by dt. On the right hand side, here we have a relation ds is less than dq by dt, or change in entropy is less than change in heat content divided by time. So here in the red block it is written that this relation is applicable for impossible processes. Entropy of any system can never be decreased. So you have to remember that expression, that entropy can never be less than the ratio of change of heat content with respect to temperature. So in the ideal case scenario, the entropy will be equal, and in the real world scenario, the entropy will always increase or will be greater than change in heat content with respect to time. So if we are calculating an entropy of a process and the value of change of entropy comes out to be less than the value of dq by t, or change of heat content with respect to temperature, then the process will represent the impossible process. So that process in the real life, that process will never happen. So for isolated system, so in the previous system we have already discussed about closed system, open system and isolated system. So in isolated system there is no energy interaction, so there is no work interaction, there is no heat interaction and there is no mass flow. So isolated system we have no energy interaction. So the same relation that we have discussed in the previous slide is written here as well. So change in entropy greater than equal to dq by dt, that is true for all processes. dq is equal to 0 because in isolated system there is no energy interaction, which include no heat transfer and no work transfer and no mass flow. So in the formula we have dq that represent change in heat content. So as there is no heat interaction, so dq will be equal to 0 and we have left ds that will be greater than 0. So as dq is equal to 0, we have two cases, either ds is equal to 0 or ds will be greater than 0. So that we will discuss that case later. So if we have ds is equal to 0, that means change in entropy is equal to 0. So the entropy remains constant throughout the process. So in point 1 it is written S is equal to constant entropy. Entropy is conserved only for reversible process. So you should remember that entropy is conserved in reversible process. For reversible process only, entropy can neither be created nor be destroyed. So that is the conservation of entropy principle, that is true for only reversible process, that entropy can neither be created nor be destroyed for reversible process. And in the second case, that is ds is greater than 0, so it means that change of entropy is greater than 0. It means entropy is increasing or changing. So entropy is increasing. Generally, entropy is not conserved. Entropy is not conserved because in real life all processes are irreversible. Therefore, the entropy is not conserved generally. Because on the left hand side you have we have studied that entropy is conserved only for reversible process. So when we will be talking about ideal cases or ideal cycle like Carnot cycle, etc., then we will be taking entropy as conserved. Whereas for real life problem, the entropy is not conserved. It represents irreversible process. So usually in the real life we have all processes are irreversible, therefore entropy will not remain conserved. So for all irreversible processes, entropy can be created but not be destroyed. So you should remember the difference between the last two statements, that for left side last statement it is only for reversible process that entropy will be conserved, whereas for irreversible process the entropy will not be conserved but it will increase. So it is here written that entropy can be created but not be destroyed, that entropy will be created or generated and will increase for irreversible processes. Here in this slide we have differentiated between reversible process and irreversible process for isolated system only. Entropy of a pure substance. Entropy of a pure substance. Entropy is an extensive property of a system. So we have already discussed about what are extensive properties, what are intensive properties. So entropy is an extensive property. Value of specific entropy are given in thermodynamic properties in the same manner as the specific volume and specific enthalpy. So as I have already discussed that usually we find the value of entropy at certain temperature pressure values from the steam table that are given at the end of your book in the annexure. So for certain temperature the value of entropy are tabulated in the table. So as you find the value of specific volume or specific enthalpy when you are solving the numerical problem, so in similar manner you will find the value of specific entropy from thermodynamic property table. In the steam tables, the entropy of saturated liquid at 0.01 degree centigrade is given the value of 0. So when we were talking about in the chapter of pure substance, I have already told you that 0.01 degree centigrade has a significant value as that is a triple point of water. All phases, solid, liquid, gas, coexist at that temperature. So as all phases coexist at that temperature, so we have referenced that value, and in steam table the value of entropy for saturated liquid is termed as 0. For many refrigerants, the entropy of saturated liquid at minus 40 degrees centigrade is assigned the value of 0. So as I have told you that refrigerant that is used in refrigeration cycle is a specially designed liquid that has properties that are very special, and for them the entropy of saturated liquid, the reference temperature is minus 40 degrees centigrade to assign the value of 0. So as in steam table the triple point of water is taken as 0.01, so for many refrigerant that is not generalized, but usually refrigerant has triple point at minus 40 degrees centigrade. So you have to remember that when we take value of entropy 0 at certain reference temperature, that reference temperature is the triple point of that particular substance. So for example, if we have a refrigerant A and we are taking entropy value at minus 40 degrees centigrade, then it means that at minus 40 degrees centigrade all three phases of that refrigerant coexist. That is not generalized for every refrigerant. This temperature may vary. So when you will go to the steam table, sometime that table will start from minus 60, sometime that table will start from minus 50, but usually minus 40 is a standard temperature at which the value of entropy is taken at 0 for many refrigerant. So here word many suggests that not applies to all refrigerants. So in saturation region, the entropy may be calculated using the quality or dryness fraction. So we have already discussed about that X is used to represent the value of quality or dryness fraction. So when we will be talking about the region that is under the dome or saturation region, so we will use that dryness fraction. So its value is 0 on saturated liquid line and 1 on saturated vapor line. So the variation of dryness fraction will be utilized to calculate the value of entropy in the saturation region. That is a mixture of liquid and vapor. So S is equal to 1 minus X SF, that is entropy at the saturated liquid line, and SD is the entropy at the saturation vapor line, and X represent the quality or dryness fraction. Increase of entropy principle. Increase of entropy principle basically states that if you consider an isolated system, because of the presence of irreversibility within the isolated system, the change in entropy is always greater than zero, or there is always an increase in entropy during such process. So if we are taking an isolated system, so there will be no energy interaction that include heat, work and mass interaction. But there is always the presence of irreversibility. So the change in entropy will always be greater than zero. And that is known as increase of entropy principle, because during such process the entropy will increase. So here we have represented del S, that is change in entropy isolated for isolated system, that is equal to S transfer, that is entropy that is transferred and plus entropy that is generated. So due to heat flow within the system, entropy will be transferred, and due to irreversibility there will be a generation of entropy. So in the second relation, the value of S transfer or entropy transfer is written by integration of change in heat content within the system divided by temperature. Plus S generation. So entropy is generated during an irreversible process. So the term S generation represents generated entropy, and that term is always present when there is a irreversibility or the process is irreversible. For reversible process, that term will be neglected out. So here it is written entropy is generated during an irreversible process, and this generation is entirely due to the presence of irreversibility. The entropy generated during the process is called entropy generation, which is represented by S generation. Here I have written the complete form S generation, but when we will be solving the problems, numerical problem, then we will write SG or SGen, SGen or SG. So we will write SGen usually, so that you will not confuse it with the entropy at saturated vapor line. So sometime in the book you will find written SG for entropy generation, but you should remember that you should differentiate that SG of entropy generation with SG, that is entropy at a saturated vapor line. So when we will be solving numerical in the during the lecture, we will use SGEN, SGen, that represent that entropy generated due to irreversible process. So the last line is, since universe is also an isolated system, therefore the entropy of the universe is also increasing. So as you know that the universe, we take universe as an isolated system, therefore we take that the entropy of that universe is always increasing. Entropy for irreversible and reversible adiabatic process. For irreversible adiabatic process, so here we have two process, irreversible adiabatic process and reversible adiabatic process. So first we will discuss about the irreversible adiabatic process. So first you should remember that adiabatic process is a process where there is no heat interaction with system and surrounding, between system and surrounding. So for irreversible adiabatic process, the generalized expression for entropy is change in entropy is equal to entropy of system plus entropy generation. So change of entropy is equal to integration dq by t. So entropy of system is mathematically represented by dq by t. We have already studied that in the previous slide, plus S generation. That S generation is the entropy that is generated due to irreversibility. We have already discussed in the previous slide. So for adiabatic process, dq is equal to 0 because there is no heat interaction. So del S or change in entropy is equal to S generation. So for irreversible adiabatic process, the change in entropy will represent the entropy generation within the system due to irreversibility of within the process. For reversible adiabatic process, so generalized expression of entropy is change in entropy is equal to system entropy plus generated entropy. So system entropy is dq by t plus entropy generated. For adiabatic process, dq is equal to 0, and for reversible process there is no entropy generation, so Sgen will be equal to 0 and del S will be equal to 0 because both terms are equal to 0 on the right hand side. So change in entropy is equal to 0. So you should remember that reversible adiabatic process is also known as isentropic process because the entropy is remain constant. So here it is written as, for reversible adiabatic process the entropy of a system remain constant and it is also known as isentropic process. The entropy of an isolated system during a process always increase, or in the limiting case of reversible process it will remain constant. In other words, it will never decrease. This is known as increase of entropy principle. So entropy of an isolated system will always increase. So usually we have irreversible reactions, irreversible process. So the entropy will be increased, and because irreversibility, due to irreversibility, S gen term will always be present, and in the limiting case, that means in the ideal scenario for reversible process, the S gen term will be equal to 0 and change in entropy will be equal to 0. For adiabatic, reversible adiabatic process, we have calculated the entropy in the previous slide, so that comes out to be constant. So change in entropy for reversible adiabatic process was 0. So that is the ideal case, but usually the value of change of entropy will be greater than 0. So this is known as increase of entropy principle. So for the term, so here in the above term we have written change of entropy will always be greater than or equal to 0. So for change of entropy less than 0, it violates the second law of thermodynamics, because second law of thermodynamics suggests that we have studied two basic principle or statement of second law of thermodynamics, that was Kelvin-Planck statement and Clausius statement, and they both suggest that if we want to convert heat into work, then there will be some amount of wastage as well, because we have to retain a certain we have to maintain two thermal reservoir. So one when heat is coming from high temperature thermal reservoir, certain amount of work will be converted and other will be rejected into low temperature thermal reservoir, that is Kelvin Planck statement. So therefore del S is less than 0, it will violate the second law of thermodynamics. So entropy of isolated system always increase and become maximum at the state of equilibrium. So that is a very important line. You should remember that the entropy will be maximum at the state of equilibrium. So here I have drawn the graphical view of entropy. So on the y-axis entropy is present, and in the x-axis you can term it as time as well. So when we are moving from left to right, so the entropy is increasing, and at certain point the entropy will be stable or constant. So at that point the change of entropy will be 0, because the process has reached its equilibrium position. So at that point equilibrium position, the value of entropy will be maximum and value of change of entropy will be 0. So here you should also remember that I have drawn the arrow. The arrow direction represents the possibility of a process, and in the left right hand side with this arrow I have written impossible. So the process will always occur from left to right, whereas if process is occurring from right to left, it means the entropy is decreasing. So the value of change of entropy will be negative. That is the violation of second law of thermodynamics. So that process is impossible. So for possible process, the value of entropy will increase and it will become maximum at the equilibrium state. So at equilibrium state, after, the value of change of entropy is equal to 0. Entropy balance. Second law of thermodynamics states that entropy can be created but it cannot be destroyed. For irreversible reaction, entropy change is equal to entropy transfer and entropy generation. So ds is equal to change of entropy is equal to S transfer plus S generation. So mechanism of entropy transfer are, so entropy can be transferred to and from a system in two forms, heat transfer and mass flow. So the term S transfer that represent entropy transfer is due to these two uh, phenomena, that is heat transfer and mass flow. Isentropic process. A process during which the entropy remains constant is called an isentropic process. For steady flow devices like compressors, turbines, pumps, heat exchangers, entropy change is zero in these devices during steady flow operation. So you should remember that when we were talking about steady flow process and when we were deriving mathematical equation for steady flow energy equation for each of these devices, we have taken entropy as constant. So for compressors, turbine, pumps and heat exchangers, there is no change in the entropy. All reversible adiabatic processes are isentropic process, but all isentropic process cannot be reversible adiabatic process. So that is also a very important line, that reversible adiabatic process is isentropic process as we have mathematically proved that in this lecture in the previous slide. But all isentropic process cannot be reversible adiabatic process. So there can be certain process that are not adiabatic process but fulfill the criteria of isentropic process. So we will be calculating the expression for other process as well in which the value of entropy is become constant. So for isentropic process, the condition is the value of change of entropy is 0 or the entropy is constant. So one of that process is also reversible adiabatic process that fulfill that criteria, that in that the entropy is constant. So reversible adiabatic is an isentropic process. But there are certain other processes as well in which when we calculate mathematically the value of entropy becomes constant and the value of change of entropy is 0. So that process also fulfills the criteria of isentropic process as well. So here is the mathematical relation. Change of entropy is entropy transfer plus entropy generation. And change of entropy of system is change of entropy transfer dq by t plus 0, as entropy generation for reversible process is 0. Note, it means that entropy is negative, but according to second law of thermodynamics, entropy can never be negative. So for irreversible process, we have del S is equal to entropy transfer plus entropy generation, and the sign negative. So here we but in the previous slide we have said that entropy can never be negative. So what is the answer? The answer is that the sum of entropy of system plus entropy of surrounding must be equal to or greater than 0. So the condition is the sum of system and surrounding. So sometimes there are processes in which the value of entropy of the system is decreasing. However, the value of entropy of the surrounding is increasing. So the overall sum will always be greater than equal to 0. So you should remember that entropy of a system can be negative, positive or 0. So for 0 it means that the process is reversible, positive if heat is adding into the system, and if Q or heat is leaving the system, then entropy will be negative. But entropy of the universe, so entropy of a universe is the sum of entropy of a system plus sum of entropy of surrounding, or change of entropy of system plus change of entropy of surrounding. The summation is the entropy of universe. So entropy of universe can either be positive or 0, but never negative. So sometime when you will be calculating the value of change of entropy, its value may come out to be less than 0 or negative. But you should remember that entropy or heat content is leaving the system and correspondingly increasing the value of entropy of the surrounding. And the overall value of entropy of universe, that is the sum of system and surrounding, is always increasing. So entropy generation is not a property of a system like entropy itself. It measures the magnitude or irreversibility during the process. So as I have told you that entropy is the property of the system, and in stream table for certain value you will find the value of entropy against different temperatures. But the term Sgen or entropy generation is arises due to irreversibility in the process. So it is not the property of the system, but it measures the magnitude of irreversibility within the process. So if we have two processes, both process move from state 1 to state 2, so PV and TS value of both are same, but there is friction involved in process 2 or any other irreversibility in process 2, so the value of entropy generation will be greater for process 2, because entropy generation represents the irreversibility of the process. So here it is written that S generation, entropy generation will be greater than 0 for all irreversible process, whereas the value of S generation will be equal to 0 for reversible process, because there is no irreversibility aspect in the reversible process. And that S gen will never be less than 0, because it represents impossible process, because it violates the second law of thermodynamics. So S generation can never be less than 0. However, you should remember that the term S system can be negative, positive or 0, that we have already discussed in the previous slide, but S gen term will always be positive or 0, but never negative. Entropy is conserved in all reversible process. So we have already discussed that, it is just a revision. And entropy is least in the solid, then entropy will be of liquid is greater than solid, and entropy of gas is maximum. So the value of entropy is greatest in the gaseous phase. So entropy of perfect solution is 0 at 0 Kelvin. And entropy of perfect crystal is 0 at 0 Kelvin. So what are perfect solution and what is perfect crystal, that we discuss in the later slide as well. So conceptual question: does Clausius say anything about the sign for uh, that is the integral sign for a cyclic process, integration sign for cyclic process, and dq is change is heat. So you should remember that what is Clausius statement. So Clausius statement was that if we want to move heat from low temperature to high temperature, we will have to supply external amount of work. So that was just to remember you the statement. So the answer of the question is no. The total heat transfer can be coming in like a heat engine, in which case it is positive. It can also be net going out like a refrigerator or heat pump, in which the case sign is negative. So sign convention, Clausius does not say about the sign for cyclic process for dq. Does the statement of Clausius requires a constant T for heat transfer as the in the Carnot cycle? So the statement was same. So so the statement of the question is, does Clausius statements required constant temperature? So in the Carnot cycle, we have there was two process, isothermal and adiabatic. So here it is asked that does Clausius statement require constant T? The answer is no. The statement for cycle involves an integration of dq by T. So here the cyclic sign that was in the previous slide. So T can vary, that is T can change, which it does during most process in actual devices. So expect except isothermal process, another process, there is a change in temperature. So most of the process in actual devices, the value of temperature will change. So here is the home assignment. You can read it, that you should go to the example problem for the topic that were discussed in during the lecture, and you should write a lecture summary report. And in the current scenario, you should email it to my email ID, that is arsalan@cietward.edu.pk. You already know, and you have submitted the previous assignment at that email ID as well. So you should go also prepare this lecture as well, because we will conduct a question session before the next online session. I will ask certain uh, topics question from these topic from this lecture. So take care. Allah Hafiz.